much, and good afternoon. And my deepest apologies for not being there in person. I was so excited to make it to Lake Geneva, and sadly we'll have to postpone that for a future trip. Nonetheless, good afternoon. My name is Emily Weber. I'm a Principal Machine Learning Specialist Solutions Architect at Amazon Web Services, and I lead our Generative AI Foundations technical field community. I've been with Amazon for 5.5 years. I've had the pleasure of working with hundreds of customers across their AI journey on AWS, and in particular specialized in distributed training and pre-training foundation models, well before it was popular, so as many of us are aware. So first I'd like to take a step back. I think that an interesting starting point in this space is actually looking at humanism. And so one of the founding figures of humanism was Francesco Petrarch. Petrarch was a 14th century poet from Italy, of course, and is noted with being sort of one of the earliest thinkers that started the Italian Renaissance. And so we look at this inspirational quote. So Petrarch tells us that love is the crowning grace of humanity, the holy to right of the soul, the golden link which binds us to duty and truth, the redeeming principle that chiefly reconciles the heart to life and is prophetic of eternal good. The reason I bring in this quote from Petrarch is because in today's world in artificial intelligence, obviously we're seeing so many different perspectives and so many different frustrations and interests, and I think a missing narrative throughout this journey that I'd like us to consider is that I believe foundation models in artificial intelligence are fundamentally a humanist project. Of course, foundation models are developed by humans. They emerge because of human creativity, because of human struggles and triumphs and passion, and whether you're looking at data sets that are, of course, created by humans, evaluation metrics that are developed by humans, applications that are designed in order to further human goals, or innovations that, again, come from human creativity. I think a narrative that's just generally missing today is about this fundamentally humanist drive throughout all of artificial intelligence. And I think this is especially true in the world of foundation models because they're leveraging, obviously, intelligence at a massive scale that has not been necessarily utilized previously. So we'll explore this today. And so in the talk today, we're going to look at foundation models revisited. We'll recover some basic steps about this and then understand what's novel and interesting. We'll talk briefly about typical ways of customizing foundation models, why these are lacking in many capabilities, some drivers for pre-training novel foundation models, so not just how to do this, but why organizations would really consider this. Some of the essential ingredients, so what you need to create a new foundation model, and the distributed training fundamentals on AWS. And on the left-hand side, of course, I did ask Stable Diffusion XL to generate an image for me. So this image is Research Center in the Swiss Alps. This was the first image that came out of STXL, and I was pretty impressed, actually. I thought that looked pretty reasonable. And so let's say, for the sake of argument, let's say I asked you to learn everything on the internet. How would you go about doing this? Now, obviously you'll say, Emily, that's impossible. It's not feasible for a single person or even a small team of people to learn everything that's on the internet. But nonetheless, let's try and get it out. So you might look at the structure of the files that are available online. You might look at the different sites, the different domains of information that are available. You try to store some of the notes. You try to store, sort of mappings between the relationships of those. But the primary obstacle, primary challenge, is just human time. Obviously, the pace of information that grows online is massive, and so it's well beyond the capabilities of what an individual human should be able to access. And so when I looked this up a couple months ago, essentially the less than 6 billion pages online, so you've got right around 6 billion pages online, and of those, the average page is read for about 52 seconds, which is a little bit depressing because you're aware that some of the content online is obviously quite dense and would be worthy of a longer read, a deeper read than that, but nonetheless 52 seconds is your average. And so that is going to take you about 83,000 hours of reading time. Now, if you factor in all of the time that humans need to sleep, that we need to eat, that we need to go on vacation, that we need to spend with our families, it's going to take you right around 41,000 human years just to read all of those pages. So for one person to take in all the information online. And of course, the foundation model is going to be able to do this in a few months. Now I say this with a caveat because naturally foundation models today aren't trained on obviously everything, but some of them may be. The public data sets that are announced are usually in the order of a few terabytes, and so they're naturally a subset of that. But nonetheless, this is the primary reason why foundation models are so powerful, why they're so interesting, why they're so exciting, is because they're leveraging these vast stores of information that are available online, which is well beyond the capabilities of what an individual human or even a team of humans is going to be able to process. Naturally, we're aware that foundation models power many different applications, and this is, as you're aware, this is because of the capability of foundation models to naturally learn a wide variety of use cases. So in traditional machine learning, 5 years ago, 10 years ago, previously, the way we would handle most learning use cases is we would set up sort of smaller, discrete models to attack each one of these. So of the 10 use cases that I have presented here, from text generation to question answering, extraction, rephrasing, and search in the language modality, and then code generation, and then a suite of image capabilities from image generation to classification, even audio and video generation. Again, previously in a discrete model world, we'd be designing an experiment and designing a model to solve one concrete task, so just one smaller task. And then the reason why the foundation model, of course, is so powerful is because it's no longer necessary to format all of the data in order to sort of fall into a bucket discretely. Now we can simply lump all of the data together into one gigantic pile and then run unsupervised pre-training through this massive pile. And then the models will then be able to naturally learn these use cases organically. Excuse me. And so this is the reason why foundation models are so powerful. Excuse me. Of course, there are many ways to customize foundation model. So there are many ways to customize foundation models. And I like to think about these in terms of their ability to increase model performance. Here, of course, accuracy is one metric. There are probably too many metrics, you can say, both too many and too few metrics to evaluate language models. But nonetheless, let's take accuracy as a candidate. And so the variety of ways to customize a foundation model, from prompt engineering, what's called retrieval augmented generation, fine-tuning, and then ultimately pre-training, these are generally known to increase accuracy sort of in the path that I'm suggesting here. And I say generally known because in the vast majority of papers that you will read on this topic, this is the sort of standard flow that is followed by most work. However, there's a flip side here, and the flip side is that as we implement a variety of these techniques and capabilities, the complexity of each capability increases and cost, of course, increases as well. And so we find this double-edged sword in the sense that on one hand, we can increase accuracy dramatically with foundation models, and we ultimately move into pre-training, but of course it becomes very complex and very expensive. And so there's a challenge that we're facing as an industry now, which is to find better, faster, less expensive ways to democratize pre-training and democratize the ability to create novel foundation models without making sacrifices on accuracy. And so I believe that pre-training might be the best long-term bet in machine learning and artificial intelligence. Many of us have been interested in pre-training for years. Of course, I still remember when BERT came out back in 2018. And I was just impressed by the courageous step that the BERT authors took to leverage unsupervised data sets. And so this trend to design models that are capable of working with massive sets of data that of course aren't naturally labeled into concrete buckets and concrete learning use cases is courageous and inspiring. So I love this trend. I wonder if the pre-trained loss functions themselves are just actually better. I wonder if they're just more intelligent than fine-tuning use cases. I wonder sort of intuitively if this is because the pre-training models, of course, are seeing everything in the data sets, and they're sort of being pushed to generate, to whether that's to complete ends of sentences or to fill in certain gaps. But there seems to be more of an open-ended creativity to this process, or a more complex learning that's happening. Whereas in the fine-tuning world, you're sort of just mapping text A to text B, or image to text. And so it's possible that this unsupervised pre-training may just actually be more intelligent than fine-tuning, just on average. And then of course when you're pre-training, you're incorporating the human-based knowledge, whether that be in the data set or in any of the other constructions of the data set. You're incorporating that into the model in a deeper way. And so when we are simply performing prompt engineering, or when we're simply performing retrieval augmented generation, or even classic fine-tuning, the knowledge that's available or that's present in the networks tends to be more at a superficial level. And so when you need to incorporate an extremely deep understanding of a data set, of a use case, of a lexicon or language that wasn't available in the online networks, and that is something that you need in your application, then pre-training appears to be a better way to just sort of anchor that knowledge at a lower level. Another reason why I continue to be optimistic about pre-training is because it's just frankly more efficient at scale when we are working with smaller machine learning models, particularly in an enterprise scenario or in an industry scenario. Then in order to make those machine learning models operational at scale, we're developing these massive machine learning operations pipelines, where you are transforming data sets at scale, training models at scale, hosting them, operationalizing them, monitoring them, retraining them, and then the sort of per model cost of working with these much smaller machine learning models become very, very high. And so pre-training foundation models, and foundation models generally, I believe are just more efficient actually than smaller machine learning models. This is because it's just easier for the limited resources that everyone has, these small teams that everyone has, these small resources that most organizations have. It's more efficient to put those in sort of one big project, which is the pre-training foundation model. So put more of them in one big project, and then use this one big project for many downstream cases. So it's actually more efficient to do this than it is to create and then manage and maintain and operationalize like tens of different smaller machine learning models. So pre-training foundation models are just more efficient at scale. And then another reason why pre-training is attractive for many organizations is because there's less legal ambiguity, actually, when organizations own the foundation model creation process, start to finish. It reduces some of the legal risk, frankly, in the sense that they own the data sets, they own the data set curation process, and of course the training process and the hosting process. And so in this way, it clarifies and it streamlines some of the capabilities for organizations. And so, as I said previously, this is sort of a generally held truth in today's AI/ML world. that pre-training tends to exceed, fine-tuning and tends to exceed the majority of prompting techniques. And so let's break this down. So of course, across the different ways that we can customize foundation models, it goes with a variety of prompt engineering techniques from zero-shot, single-shot to few-shot prompting. Each of these is generally known to increase model performance. And this is the same across computer vision, across language, across smaller and larger data sets. And then naturally, of course, we're seeing a variety of ways to perform parameter efficient fine-tuning, which is naturally very exciting. With classic fine-tuning still coming out on top in smaller cases. So parameter efficient fine-tuning is getting better and better, which is an exciting trend because it's so computationally efficient, makes it more accessible to more developers. And then the belief, the hope, the thinking is that pre-training generally will fill this gap. And so this is why most organizations explore fine-tuning, because it's generally held to be more accurate at the end of the day than classic fine-tuning. And so what does it take? What are some of the ingredients to pre-train a new foundation model? So here are 3 foundation models that were pre-trained on SageMaker. And so Stable Diffusion 2.1 was trained with 5 billion image text pairs, clocking around 240 terabytes on disk. So of course this is truly a massive data set. What's interesting is that computer vision data sets tend to be much larger than their language pairs. However, the sizes of the models tend to be much smaller. Now with SDXL, this is changing slightly. The model sizes are somewhat larger in SDXL, but they're still nowhere near the size of the massive tens of billions and hundreds of billions of scales that we see in language. Stable Diffusion was trained on 32 P4D instances on AWS, on SageMaker, and then the time to train for this model took about a month, right? That took 28 days. And then 2 language models for you. So Falcon 40B, of course developed by the Technology Innovation Institute, is about 1 trillion tokens in data set size, which on disk takes you just under 3 terabytes. This is about 40 billion parameters, looking at 48 P40 instances, around 2 months to train. And then another model that I'm quite fond of is Bloomberg GPT. And so Falcon was designed to be, of course, a general language model across sort of open source data sets that were very highly curated by removing duplicates. And then Bloomberg GPT is, of course, a financial data set. So Bloomberg wanted to develop a novel foundation model that's better suited for financial use cases, such that they could leverage in their applications and in their stacks. And so Bloomberg GPT trained with 700 billion tokens, right around 2 terabytes on disk, about 50 billion parameters. So again, not a language model to answer every question under the sun, but certainly a language model to answer financial questions quite well. This was a very large cluster size, about 64 P4D instances. This is many tens of accelerators, many hundreds of accelerators, and just under 2 months. And so we can see here that generally pre-training novel foundation models, of course, requires lots of data. If we're interested in language, this is something in the multiple terabytes of data sets, and then if we're looking at images, this can be many hundreds of terabytes. And then, of course, the necessary ingredients are large instances and a large accelerator, large cluster sizes, and then just sheer time to train these. And so I work with customers who explore creating novel foundation models because they see the benefits of pre-training in order to solve accuracy problems at work. This is because while the foundation models that are available based on images and text trained online, while they're very powerful in sort of general use cases and general knowledge understanding, they tend to underperform actually when faced with the complexity of the real world. So, for example, if you have hundreds of thousands of screws, like physical screws, and you have more than 100,000 different types of these screws, a language model isn't actually going to be able to understand the nuances of these things. And so the search space for many real-world problems is actually much larger than Wikipedia, or it's much larger than content that's available online. And so as a result, companies are exploring creating their own foundation models in order to solve these accuracy problems. However, when I'm working with these companies, when I'm working with these organizations, this is sort of the primary experiment that I try to help them set up, such that they can mitigate the downside risk of this not going anywhere and make sure that they're creating a foundation model that's actually adding value to their organization. So I like to set it up like this. So again, we're going to look at some type of accuracy KPI here. This is a fine-tuned KPI. So if we're caring primarily about text classification, then this could well be downstream accuracy. If we care about summarization, this is going to be more like a Rouge, question answering, etc. And so we'll take two models. We'll take one open source model. This might be a GPTJ, 6 billion parameter model, and then we'll pair this with a novel model that your team has pre-trained. However, this is going to be a pre-training experiment at a tiny subset of your data. So certainly not the entirety of the data set, not all of the terabytes, but something large enough to still see an impact, but small enough that that you're again not breaking the bank basically. And so the experiment that we'll set up is of course using the open source model on one hand, and then using your pre-trained model on the other hand, and then we'll fine-tune both of these. So we'll fine-tune both of the models on the downstream tasks that you care the most about, and then observe their performance. And essentially, the signal that you should be able to see before you go launch all of those accelerators, and before you run up a massive cost for creating this novel foundation model, is you should be able to see performance gains, again, on your pre-trained model. So your pre-trained model should be able to beat this open source model, even at a small data set. And then after you've proven this, you're ready to design the entire experiment. And so how do we do this? How do we pre-train foundation models on AWS, assuming we want to, and assuming we have a business case and data sets? So at a high level, of course, it's conceptually quite simple. Implementing it is far from. So obviously the first step is to simply gather and store large data sets. This is, again, for language in multiple terabytes. For vision, this can be hundreds of terabytes. And then naturally, this doesn't need to be labeled. So we're able to just use large data sets, of course, that are unlabeled. It's still necessary to curate the data sets and essentially perform deduplication and ensure that the data are high quality. Once we've stored them, of course, we'll need to process them for training, whether that's creating novel tokenizers, and then tokenizing them at scale, again, running deduplication. I like to make heavy use of what's called job parallelism and CPU-based work for this data set pre-processing. This is because CPUs are, of course, a fraction of the cost of GPUs, and so they're quite handy for this data set pre-processing. Once we've done this, then of course we'll need to optimize the data storage for training runs. I'm quite fond of using what's called FSX Luster, which is a managed dataset storage option on AWS that integrates nicely with training service that we have what's called SageMaker for training. And then once we've optimized our data storage, we'll develop and test training scripts, and it's quite handy, again, in step 4 here, to start with very small instances. Start with very small CPUs, very small GPUs. You can use older GPUs, you can use smaller GPUs, use less expensive instances, and use those for your early stage iteration and development. So when you're building your core training loop, when you're making sure the training loop works, when you're running it on multiple accelerators. It's so handy, again, to do that on the smallest instances that you can, because that keeps costs down. Once you've developed a training loop and are happy with it, then the next stage in step 5 is to scale this up all the way, to actually go to the height of your vision, to the height of your aspiration. Oh, looks like the screen stopped sharing. 1 second. My goodness, I think I'm out of time. That was very fast, nonetheless. And then once you've designed this, then it's helpful to implement this in stages. So I like to provide a number of stages for customers to build towards, using increasingly larger sizes and larger samples of their data sets. And so a few final call to actions for you. I realize this one quite quickly. I do have a book that's available on this topic.